Hello again. On this video, we're gonna discuss the following problem. So first, we have the set of all function. I don't know whether it is a set or not. So this collection of all function from real to real, and then C be a subset of F. Just take all the continuous function, and we would like to show that the cardinality of all continuous function is exactly the same as the cardinality of the real number. But the cardinality of the collection of all function is strictly bigger than the cardinality of the reals. Okay? So in order to prove this, we will take for granted several results. So first of all, we will consider this as fact that the cardinality of the real is exactly the same as the cardinality of 2 to the n. So whenever we write down a to b, it is the collection of all functions from b to n. Okay. But whenever we have the power like this to be the natural number, so we can think of as the collection of all sequence where the entries coming from the base. So like this one can be think of as the collection of all the collection of all sequences, so that the entries are either 0 or 1. Okay. So we'll just use this. Okay. So first of all, we need several lemma. We will show that if the cardinality of A is equal to the cardinality of, say, C, then the cardinality of A to the B is the same as C to the B. Okay. I think this one is easier than the other way around when we replace the B with some other set with the same cardinality. So I think I will leave this for the reader. Okay. Second lemma, if B, the cardinality of B is the same as the cardinality of C, then the cardinality of A to the B is the same as A to the C. Okay. So how are we gonna prove this? So probably we'll just give some sketch of proof. So given a map from B to A, we would like to come up with a map from C to A. So how do we map this to get a map from C to A? So since B and C have the same cardinality, we have a bijection from B to C, or from C to B. So let alpha be one of the bijection, be a bijection. So we have from B to C, right? Or from C to B. It's better to consider from C to B, isn't it? Right? Because then we can compose in order to make a map from C to A. So let's say, now if we want to have, let's say we are given this map and we would like to create a map from C to A. Okay. So we have from C to B, which is alpha. And then in order to have a map from C to A, we just compose alpha with F. Okay? So just define a map from F to alpha F alpha. Okay. And just show that this map is indeed a projection from the collection of all maps from B to A to all the collection from the map. All maps from C to A. So let's give it a try. I think that shouldn't be too difficult, but we never know until we try, right? So let's say we want to show that this assignment is injective. So suppose we have two functions here, let's say f and h, such that the map of f and h are the same. So suppose f composed with alpha is the same as h composed with alpha. I don't know. You read it alpha composed with f probably, that's the more correct way. Okay, so we want to see whether f is equal to h. If they are indeed the same, then we know this assignment is an injection, right? But okay, so it means that f of alpha c is the same as g of alpha c for every c in C. But alpha c is exactly what? Exactly b, because this map is bijective. So this will follow that f of b is equal to g of b for all b. I think it's h. Sorry. Hence f is equal to h. So the assignment is an injection. And the next question is whether this assignment is surjective. So given a map from G to C to A, we would like to come up with a certain map so that the composition of a map from B to A with alpha is equal to G itself. So of course, the obvious choice is pick G composed with alpha inverse. Right? Let's check if this makes sense. So the alpha inverse goes from B to C. Then if we compose alpha inverse with G, we come up with a map from B to A. Right? So this is a map from B to A. Then if we compose this with alpha, we get A to G. This tells us that G alpha inverse is assigned to G, which means that this G has a preimage in A to the power of B. So the map is surjective. So therefore this lemma is correct, right? Great. So the next lemma is that the cardinality of A to the power of B cross C is equal to the cardinality of this set to the power of C. Okay. So let's find out if this lemma is natural. So let's let's start with a map from B cross C to A. Is there a natural way to come up with a map from C? So, I don't know, let's say F hat. How to create an F hat, which is a map from C to A to the B. Right? Or the other way around. We start with this and we come up with this. Right? So that's our choice. So I don't know which one is a better approach, whether it is from here to here or from where to where. Okay, so for every B in capital B and little c in capital C, we have f of BC, which is a member of A. So then we can think of f for each B. For each B, the FB dash from C to A is a map from C to A, right? Okay. But what we want is a map from C to A to the power of B. So our purpose is, given an element of C, we want to come up with a function from B to A, right? So let's define the C as follows. Given C, okay. So let's call this as FB. Okay, this is just FB, right? We call this FB. So it means we have F. Hold on, this is okay. So we want to have a map from B to A, right? So given a B, it's gonna be F dash FBC. Okay. Now we need to think of how this is like this, F dash C. Okay. This is a map from B to A. Okay. So I think probably we don't really need this, right? Okay. So given the map from B cross C to A, define a new map, let's say F hat, that take any value of C to the value of F of dash of C. So this is going to be a function, let me say that. This is going to be a function from F dash C is a function from B to A, right? Okay, so now we just need to check whether this map is injective and surjective. Okay. So let's say we have, we take two maps here such that the image are the same. So that FG in A to the power of B cross C such that F hat is equal to G hat. What does it mean that F hat is equal to G hat? Remember, they are a map from B to A. So it means that, okay, so this one is a map from C to A to the power of B. And for all C in C, f hat c is equal to g hat c. But what does it mean? It means that f dash c is equal to g dash c as a map from B to A. But if the two are equal as a map from B to A, then f of BC is equal to g of BC for all B and also for all C and C. Okay? But if f of B of C is equal to g BC for all B and C, then therefore f is equal to g. Thus, f is equal to g. So the assignment f to f hat is injective. Okay. Now we just need to check that the assignment is surjective. So given map from, let's say H from C to B. Okay. We want to come up with a map from B cross C to A, so that under this assignment, this f hat is exactly this H, right? So for which f, that this H is equal to f tilde, f hat, whatever. Okay. So what this H does, so for every C, HC is a map from B to A. So think of this H under script C as the image of C under H. Okay. Okay, so now what? We would like to find F. What is the F? From B to C to A. So for every C, for any C, we want to find this F. Remember? So we don't have the definition of F yet. So we define F so that F dash C is equal to HC, right? So we are allowed to do that. Okay, so then by using this definition, we can have we can have a map from B cross C to A. So how do we define a map? So f of BC is equal to HC of B. Okay. So here's how we define our f. Okay. And then we will just need to show that for this particular f, that f hat is equal to H, right? Okay, I think we don't need to write this down. So define this by this. So how do we define again the f hat? F hat is a map from C to A cross B. Remember? So then we just need to check that f hat of C is equal to H of C for every. So f hat C is equal to f dash C, right? Okay. So now let us check whether this f dash C is equal to HC. right? So again, we want to see if f hat is equal to h, right? Okay, so let's compare. hc is equal to hc. Now since hc is equal to f vc, then hc is equal to f dash c as a map from where to where? From B to A. Okay. Okay, and this is true for all C. For all C. Okay. What's this? Then h of C is equal to f delta C for all C. Therefore, h is equal to f delta. Right? Therefore, the map is surjective. Okay, so then we have this result. Right? Now, how do we use all the lemmas to prove our claim? So, first of all, notice that if we have a continuous function, okay, we can have an injection from the set of all continuous functions to the set of all sequences where each term is rational. So how do we make a map? If we are given a continuous map from R to R, then we find, so let's say R1, R2, R3 and so on is an enumeration of Q. Remember the fact that we can have a bijection between Q and N means that we can enumerate elements of Q by, we can indexing elements of Q by natural numbers. So we can tell which one is the first rational, the second, the third, and so on. So let's line up all elements of Q as follows. And then from this, from all the list of rational number, then we can have a sequence. I'm sorry, this is supposed to be, this should be the sequence with terms are real, right? So look at this, FRI, right? So each of this is a real number, right? So this must be a sequence, a real sequence, right? So why this assignment is an injection? If we have two functions, two continuous functions which are agree on the rational, then by taking the limits, they will agree on all the real numbers. So if FRI is equal to G of Ri for all I, then Fx is equal to G of X for all X in the number. Why is that so? So just find a rational sequence that converges to X. Okay? Since f is continuous, then the value of fx is the same as the limit of the value of f of Ri. But since f of Ri is the same as g of Ri, then that limit has to be the same. Therefore, f of x is equal to g of x. Okay? So then this map is an injection, which tells us that the cardinality of C is less or equal to the cardinality of N. Right? Now, we will use the fact that the cardinality of R is the same as the cardinality of 2 to the n. So this is exactly the same as. Why can we use that? Remember that before we have a lemma which says that if the cardinality of A is the same as the cardinality of B, then the cardinality of A to the C is the same as the cardinality of B to the C. Right? That's exactly what we are using here. Since the cardinality of R is the same as the cardinality of 2 to the n. Okay? But then, according to this lemma, this cardinality is the same as the cardinality of 2 to the n cross n. Okay? And then the other lemma that we didn't prove says that if cardinality of B is the same as the cardinality of C, then the cardinality of A to the B is the same as the cardinality of A to the C. Since the cardinality of n cross n is the same as the cardinality of n, then this cardinality is the same as the cardinality of 2 to the n, which is the cardinality of the reals. Okay? So we know that the cardinality of all continuous function is less or equal than the cardinality of R. Okay? Now, for the other way around, we can have an injection from C to R. I'm sorry, from R to C. From R to C. Which is given every x or whatever. Z here. Okay. Then we can have a continuous map which is a constant map. Constant map f of R is equal to Z for all R in real. Okay. So given a real number Z, from that real number we can construct a continuous function which is a constant continuous function with Z as its value. Okay. So this is clearly an injection as well. Right? Okay. So therefore from this assignment we know that the cardinality of R is less or equal to the cardinality of C. Okay. Combining these two results, then we have the cardinality of C is exactly the cardinality of R. So thus, cardinality of C is the same as the cardinality of R. Okay. Now, how can we show that the cardinality of the collection of all functions is strictly bigger than the cardinality of R? Okay. So we are going to use the following result. We're going to take it for granted that there is no surjection map, or the cardinality for any set is strictly smaller than the cardinality of its power set. Okay, that's a fact, and we can prove it. Okay, so then how can we see now that the cardinality of C is strictly less than the cardinality of F? Okay, so compare the F and 2 to the R. So we know from this fact that the cardinality of R is strictly less than the cardinality of 2R. We are going to show that the cardinality of 2 to the R is strictly smaller. No, not necessarily strictly smaller, but less or equal to the cardinality of F. So we're going to make an injection from 2 to the R to F. Okay? And that's easy, right? Because remember that 2 to the r is, let me explain again. We would like to show that the cardinality of 2 to the r is less or equal to the cardinality of all collection of all collection of functions from r to r, right? So then we need to make an injection from 2 to the r to f. And this guy is nothing but the collection of all maps from r to 2, right? So this thing is, in fact, is a subset of this, right? So let me rephrase again. The 2 to the r is a collection of map from r to 0, 1. Okay. Meanwhile, f is the set of all functions from r to r. So clearly this guy is a subset of this, therefore the cardinality of 2 to the r is less or equal to the cardinality of f. And in particular, since the cardinality of this 2 to the r is less than this, then the cardinality of c, which is the same as the cardinality of r, is less than the cardinality of 2 to the r, less or equal to the cardinality. And we are done. Okay, so thank you for watching. See you again in the next video. Alright.